Okay, for direct imaging, the same thing. You use the same objective to excite the source sphere and to capture the image. So you have your spectral filter here, you have your excitation wavelength going through the objective, propagating through the chain, exciting the source sphere, which then re-emits, and then light propagates through and you capture the image. Here is a plot of the full width half max of the beam for different sphere numbers, and it's directly compared to the scattered imaging technique. As you can see, they demonstrate similar trends, so that means that the scattering imaging technique is valid, which is what I'll use for the rest of these studies because it does make it easier. Okay, first I would like to thank Oris Daracius from this point on because all the modeling results that were used were obtained from him, and then also the experimental work I performed was guided by his modeling results. So this is microsphere arrays which are integrated into microcapillaries. For some laser surgery applications, you need a flexible delivery system. Like in the case of diabetic retinopathy, they have fibrotic membranes which are forming above the retinal tissue that block their vision. So the general procedure to remove those now is using a mechanical pick or tool and poking a hole through the sclera to remove this, which causes a lot of collateral damage such as intraocular bleeding. So if you could find a more non-invasive way that maybe you could cut down on some of that collateral damage, maybe by making some multimodal focusing microprobe for precision, as a precision laser scalpel. What you would need out of this is a flexible delivery system, precise spatial and depth control. So the depth control could be provided. First, you need to use a wavelength of light that is coupled into the tissue that you're wanting to get rid of, or the fibrotic membrane. And then, so in that, for this application, it's 3 microns. And then 3 microns is also strongly absorbed, so that gives you some level of depth control. So if we consider a conventional single lens microprobe of relatively low index, or 1.5 for example, and then a single mode fiber, the result of this is you're going to have a long working distance. And then also, because of this long working distance, when it's placed in an aqueous medium, it kind of can't preserve its focusing effects. It's going to lose those focusing effects. Also, for the wavelength chosen for this application, 3 micron, it's not supported by single mode fibers. So if you look at a slightly modified microprobe where you use higher index of refraction so that you can get focusing along the back surface of the sphere, that way you can preserve your focusing effects in an aqueous medium, and then also use a hollow waveguide because the wavelength that you chose to get the depth control and still be able to get rid of the fibrotic membrane. You can use the hollow waveguide because since that wavelength isn't supported by a single mode fiber. But as you can imagine, with a wavelength 3 micron, diameter of the hollow waveguide on the order of 300 microns, and it may be on the order of millimeters or a meter long, you're going to have a lot of higher order modes propagating in this. So in the ray tracing model here, you're going to have a lot of Marodnal and skew rays, and they're going to be focused respectively on the backside of the surface. The overlap of these focal spots are going to give you a very broad spot, which may be too large for the application. So now, if you have a microsphere array integrated inside of this tubing, you could you would have the depth control because you'd be able to use the hollow waveguide at 3 micron, where the light would be strongly absorbed. You could choose a proper index So the focusing is provided at the backside of the surface to give you the spatial control and be able to use in contact mode along with preserving your focusing. And then the chain of microspheres can filter out some of these Maragndon and skew rays so that you have a reduction in spot size. We also modeled the optical transport in these chains. This figure here is an attenuation plot as a function of sphere index, and this is for the portion of the 15th to 20th sphere. And as you can see, there's a local minima here in the attenuation per sphere, and that's corresponding to periodic focusing. Okay, we wanted to experimentally verify or test this modeling, so some sort of prototype or device had to be fabricated. So you put you micro-manipulate a sphere to the end of the tubing, use a micro-manipulation tool to push the sphere to your desired length, and then you just pack in the number of desired spheres, and that's shown here. Okay, and here we have an experimental comparison of attenuation with modeling. The modeling was done by ZMAX, it's a ray tracing program. So in order for it to properly fit the model, we had to use a sphere diameter comparable to the ratio, which is very large. So here, this is a 50 micron sphere diameter. We were using visible light, so it was approximately 100 times, the diameter of the sphere was approximately 100 times larger than the wavelength of light. So the ray model should be valid here. And our experimental results coincided with the model, so that was good. So in conclusion, you can use microsphere arrays integrated into microcapillaries and develop some sort of microprobe which has good spatial and depth control. Okay, the next portion of my thesis was dealing with focusing and transport of optical beams in chains of spheres spanning physical and geometrical optics. There's been some interest in this field lately, especially with the study of novel optical modes and optical transport in these structures. Before I start talking about focusing and attenuation in geometrical optics, I would like to say that the diameter of the spheres and the physical size of these structures that I'm trying to compare are varying. So it's important to normalize these results so that you can compare the trends of these structures. And then this is modeling which was done by Orish for in the geometrical optics case. And in geometrical optics, things scale. So if you have in the periaxial, if you have periaxial light incident on a sphere of index 2, it's going to focus on the backside of the sphere. If you increase the sphere diameter, the focal spot's still going to be at the same portion. So the main thing is that the optical properties scale for geometrical optics. So this plot here is the spot size normalized by the sphere diameter. The black curve is just the single sphere case. The green curve is 5, the blue curve is 10 spheres, and the red curve is 20 spheres. By looking at this plot, you can tell that there is some focusing effects happening in this region from roughly 1.7 to 1.9 index of refraction. And then in that same region here for the attenuation, you can see a local minima. So we can say that these focusing effects lead to smaller attenuation, or periodic focusing effects are leading to smaller attenuation. I was using spheres that had an index of 1.59 polystyrene, and it was the didope sphere case, and it was emitting green light, so roughly half of a micron. And the geometrical model does not predict focusing at this index. And I used 30 micron and 10 micron. So d over lambda is greater than 20. So then I observed their focusing effects. The way that I looked at their focusing effects is I normalized the focus spot after some sphere by the focus spot after the first sphere. And if you look here, you can see that the experimental results coincide with the modeling from ray tracing and geometrical optics regime, which show that we shouldn't have focusing. However, if you bring the scale down and you look at smaller sphere diameters, you start to have this drastic beam tapering effect for wavelength scale spheres, which is not predicted by the geometrical model. I also looked at the attenuation results for these wavelength scale spheres. In geometrical optics, once again, these properties should scale. However, you can see here that there's a relationship between the diameter of the sphere and the attenuation plot. So the smaller the sphere diameter, the less attenuation. And then if you look at this plot here, this is the black curve is the geometrical model of attenuation as a function of index for a portion of the chain from the 16th sphere to the 20th sphere. And remember, we had focusing for 1.59. In geometrical optics, you had focusing at this dip. And you can see that we had more drastic focusing effects, and then also you have less attenuation than what the geometrical model predicted. But the geometrical model did predict focusing for certain indices. So the